Hi everyone, today we're doing our first set of notes for college statistics on sections 1.1 and 1.2. 1.1 is all about what is statistics. Statistics is used for making decisions when we are faced with unknowns or uncertainties. It enables us to look at a small group of people or items and infer the effect on a larger population. Statistics is the study of how to collect, organize, and analyze and interpret numerical information from data. It's both the science of uncertainty and technology of extracting information from data. Individuals are people or objects included in the study. Variable is a characteristic of the individual to be measured and observed. Now we have two types of variables. First, we have a quantitative variable, and this has a value or numerical measurement. Addition or averaging makes sense. So if you're thinking quantitative, it's like a quantity, which is a numerical measurement. Qualitative variable is our other type, describes an individual by placing the individual into a category or group. So qualitative, think quality. We have population data. This is data from every individual of interest. It's fixed and complete. We have sample data, and this is from only some of the individuals of interest. It may vary, and it's not complete. So, a population parameter is a numerical measure that describes an aspect of a population. A sample statistic is a numerical measure that describes an aspect of a sample. If you notice, population and parameter both start with P, sample and statistic both start with S, so you can use that to help you with remembering that a parameter goes with a population and a statistic goes with a sample. Here's our first question. How important is music education in school? The Harris Poll did an online survey of 2,286 adults age 18 and older within the United States. Among the many questions, the survey asked if the respondents agreed or disagreed with the statement, learning and habits from music education equip people to do better team players or to be better team players in their careers. In the most recent survey, 71% of the study participants agreed with the statement. I would like you to answer these questions A through E, and then we'll go over them in a few minutes. Okay, identify the individuals of study and the variable. So the individuals are the 2,286 adults, and the variable is whether they agree or disagree with the statement. Do the data comprise a sample? If so, what is the underlying population? So yes, this does describe a sample. The population is all U.S. adults that are 18 or older. Is the variable qualitative or quantitative? This one is qualitative because we're asking if they agree or disagree. So that's going into a category of agreeing or disagreeing. Identify a quantitative variable that might be of interest. So this could be something like income, years of experience with music education. It could be age, your number of kids, or the number of instruments you play. is the proportion of respondents in the sample who agree with the statement regarding music education and effect on careers a statistic or a parameter. So this is a statistic because the proportion is computed from sample data. Okay. Here's the next question. Ecology, wetlands. The government agencies carefully monitor water quality and its effect on wetlands. Of particular concern is the concentration of nitrogen in the water draining from fertilized lands. Too much nitrogen can kill fish and wildlife. 28 samples of water were taken at random from a lake. The nitrogen concentration, milligrams of nitrogen per liter of water, was determined for each sample. So I want you to answer these questions, and then we'll go over them in a few minutes. Okay, identify the variable. The variable here is the nitrogen concentration. And this is milligrams of nitrogen per liter of water. Is the variable quantitative or qualitative? This one is quantitative. And what is the implied population? This would be all the water in the lake. We have two more definitions to finish up this sentence. Descriptive statistics. This is methods of organizing, picturing, pricing, and summarizing information, samples, and populations. Inferential statistics is methods of using information from a sample and populations. And we'll be discussing these in more detail in later chapters. Our next section for today is 1.2, random samples. So a simple random sample of n measurements from a population is a subset of the population selected. Every sample n must have an equal chance of being picked. No research or bias occurs in the items selected, and it may not always reflect the diversity for the sample. So how to select a random sample? Let's say we want to choose a sample of 10 from a population of 100. One way to do this would be to number the 100 by assigning each a number from 1 to 100, then putting 100 pieces of paper in a hat, each with one of the numbers on it, and drawing 10 of the numbers. This is a valid way of selecting a random sample, but the larger the population gets, the less practical this method becomes. So here's our first question. It says, is open space around metropolitan areas important? Players of the Colorado Lottery might think so, since some of the proceeds of the game go to fund open space and outdoor recreational space. To play the game, you pay $1 and choose any 6 different numbers from the group of numbers 1 through 42. If your group of 6 numbers matches the winning group of 6 numbers selected by simple random sampling, then you are a winner of a grand prize of at least $1.5 million. So this question says, is the number 25 as likely to be selected in the winning group of 6 numbers as the number 5? And this one is yes. We know that it says you pay $1 and you choose any 6 different numbers, and then they are chosen. So 25 is just as likely to be chosen as the number 5. Could all the winning numbers be even? Answer here is also yes. Even numbers are just as likely to be chosen as odd numbers. Your friend always plays the numbers 1, 2, 3, 4, 5, 6. Could she ever win? Yes, again. Those numbers are just as likely to be picked as the numbers 42, 41, 40, 39, 38, 37. Another way to use random numbers or digits, everyone will receive a copy of the table of random digits. This I actually uploaded. It's on Schoology for you. Starting at any point of the random digits, start reading off 2-digit numbers. For example, if we start on line 106 of the table, we get this set of numbers. So we want to divide these into 2-digit numbers. So I'm going to draw lines here to split these into 2-digit numbers. Okay. And so that says this becomes, I'm going to list all the numbers that we have here. So we have 68, 41, 73, 50, 13, 15, 52, 97, 27, 65, 85, 8, 95, 70, 67, 50, 21, 14, 74, and 87. All right, and so the 6 we select for our sample are those numbers. So now we have to think. Remember, it said the lottery is the numbers 1 through 42. Now we want to make sure these are all 2-digit numbers. So I'm going to actually label this as 01 to 42 to make sure each number has 2 digits. So the 6 we would select from our sample, 68 is too high. 41 is good, so I'm going to list that. 73, too high. 50, too high. 13 and 15 are both good. So we're halfway through our sample. 52 is too high. 97 is too high. 27 fits within our range. 65 is too high. 85 is too high. Then we have 8, which is good. So you can write 08 or just 8. 95 is too high. 70 is too high. 67 is too high. 50 is too high. And then we have 21 for our 6th number. So we stop here because we've already found the 6 that we want. Suppose we have a population of 834 and we would like to select a random sample of 8 from this population. We can assign the numbers 001 through 834. So again, I'm going to write this bigger here. To the population. Notice it here, if we get the numbers 835 through 999 or 000 from our random numbers, we will ignore this and move on. This way the selection is fair. If instead we said that all these numbers correspond to the individual 834, then this individual would be much more likely to be chosen than the others, and the sample would not be fair. So starting on row 109 of the random number table, here's the digits we get. So now we need to divide these into 3-digit numbers. Okay, so these are split into 3-digit numbers, and we need to choose the ones that fit our sample between 1 and 834. So I'm just going to use this list we have here. 360 is good. And this time we want to select 8 of them. We have 91 is good, so you can write 091 or just 91. 936 is too big. Then we have 515. We have 412 is good. 396 is good. 388 works. 545 is within our range. And then we have 346. And again, we can stop here because that gives us 8 that we want. Note, if this process turns up duplicates, for example, if we had 515 and then another 515 later, then we simply ignore the second 515 and keep going. We do not select the 515th individual twice for the sample. All right, so this says use the table of random digits starting at line 136 to generate a list of 6 random numbers from 1 to 8,615. Explain your work. So let's start this one together. So first, let's talk about what we're going to do. We want to choose 6 random numbers. So we're going to choose 6 numbers that are between, and we want to be from 1 to 8,615. But remember, these have to have the same number of digits. So I'm going to write 0001 and 8,615. We're going to group the numbers by 4 digits then. And we're going to ignore numbers outside the range and duplicates. Okay, so if we are looking at our table of random digits starting at line 136, when we go to list these, we are going to start with 08421. Then we have 44753, 77377, 28744, 75592, 08563. So I'm going to stop there. This should be enough for us. So I want you to go through, follow our rule. I want you to group these numbers by 4 digits. And I want you to choose the 6 numbers for the sample. And then we'll go over this in a few minutes. Okay, we're splitting these in groups of 4. So I'm going to draw some lines here, dividing them by every 4 digits. Okay, so first we have this number, 842. That fits within our range. Then we have 1,447. That works. Our next one's also good, 5,377. Our next one's also good, 3,772. The next number is 8,744, so that's too big. Then we have our number 7,559. And last but not least, we have 2,085. So this was just enough for this one. So those are your 6 random numbers. A simulation. This is a numerical imitation of a real-world phenomenon. We can use similar method to random sampling to simulate a process such as tossing a coin or rolling a die. The important thing when we do this is that in our simulation, the outcomes are exactly as likely as the outcomes in the event we are simulating. Suppose we want to toss a coin 10 times and see how many times it comes up heads. We do not have a coin, but we do have a list of random digits. Since there are 2 outcomes, heads and tails, and each outcome is equally likely, assuming the coin is fair, then we can divide the 10 digits 0 through 9 into 2 groups of 5 and say that each group corresponds to heads or tails. For example, we could declare that the numbers 0, 1, 2, 3, and 4 are heads, and 5, 6, 7, 8, 9 are tails. then the following random digits would give us a sequence of tosses of, so let's figure this out. We want 10 coin tosses. So 10 stops here. And so let's think. Anything again, 0 through 4 is heads, 5 through 9 is tails. So this is going to give us tails, 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 heads, heads, tails, 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 heads, heads. So here we had 4 heads and 6 tails. Now, just a note, we could have chosen different groups. For example, 0, 2, 4, 6, 8 could be heads and 1, 3, 5, 7, 9 tails. What matters is that both groups are equally likely. So grouping like 0, 1, 2, 3, 4, 5, 6, 7 heads and 8, 9 tails would not be an accurate simulation because in the simulation, heads is much more likely than tails. Now, suppose that we want to simulate 8 rolls of a fair 6-sided die using random digits. We can declare that the digit 1 corresponds to rolling a 1, 2 corresponds to a 2, and so on up to 6. There are only 4 other digits, and so there's no fair way to allocate them to the outcomes like we did in example 1 above. If we say that 7 corresponds to 1, 8 to 2, 9 to 3, and 0 to 4, then these outcomes are now more likely than rolling a 5 or a 6. Instead, we simply ignore the digits 7, 8, 9, and 0 in order to make sure the simulation is accurate. So, given these random numbers, we have to figure out what are our 8 rolls. So, let's go through and look. If I'm marking my digits as we roll here, 8 we ignore, 0 we ignore, 8 we ignore, 2 is good, so I can count this one. So that's going to count as our first roll. 4 is also good. We count that, so that's our second roll. 1 counts. 6 counts. 4 counts. Then we have another 8, which we ignore. 2 will count. 5 will count. 8 we ignore. And then we have one more 5. Okay, so again, our rolls are going to correspond to which ones count. We will not count the ones that we ignored as a roll. All right, so now it says use the table of random digits to simulate the outcomes of tossing a balance that is fair penny 10 times. So let's think. How many outcomes are possible when you toss a coin once? There's going to be 2, right? Heads or tails. There are several ways to assign numbers to the 2 outcomes. Because we assume a fair coin, we can assign 0 and an even digit to the outcome heads and an odd digit to the outcome tails. Excuse me. Then starting at block 3 of line 120 of the table of random digits, I want you to list the first 10 single digits and then answer these questions C and D that follow, please. Okay, so as a reminder, we said 0, 2, 4, 6, and 8. These are our heads. And then 1, 3, 5, 7, 9 are our tails. So if I go to block 3 of line 120 of the table of random digits, the first 10 digits, we have 3, 9, 4, 2, 1, and then 6, 5, 8, 5, 0. You'll notice these are putting groups of 5 on the table, so that way it's easier for you when you go to copy these. So what are the outcomes associated with the 10 digits? So let's list them. We have tails, tails, heads, heads, tails, heads, tails, heads, tails, heads. So we have 5 heads here and 5 tails. If you start in a different block and row of the table of random digits, will you get the same sequence of outcomes? And the answer here is no, because it's a table of random digits. All right, last we have different types of sampling. So, random sampling uses a simple random sample from the entire population. Stratified sampling is when you divide the entire population into distinct subgroups called strata. The strata are based on a specific characteristic such as age, income, education level, and so on. All members of a stratum share the specific characteristics, and you draw random samples from each stratum. Systematic sampling is when you number all members of the population sequentially. Then, from a starting point selected at random, include every kth member of the population in the sample. So every third person or every 100th person. Cluster sampling. You divide the entire population into pre-existing segments or clusters. The clusters are often geographic. Make a random selection of clusters and include every member of each selected cluster in the sample. Multi-stage sampling is using a variety of sampling methods to create successively smaller groups at each stage. The final sample consists of clusters. Convenience sampling is when you create a sample by using data from population members that are readily available, such as the first few people that walk through a door or everyone in your class. All right, so our last practice, Modern Managed Hospitals, MMH, is a national for-profit chain of hospitals. Management wants to survey patients discharged this past year to obtain patient satisfaction profiles. They wish to use a sample of such patients. Several sampling techniques are described below. Categorize each technique as simple random sample, stratified sample, systematic sample, cluster sample, or convenience sample. Go ahead, take a few minutes, and then we'll go over these ones. Okay, A says obtain a list of patients discharged from all MMH facilities. Divide the patients according to length of hospital stay, 2 days or less, 3 to 7 days, 8 to 14 days, or more than 14 days. Draw a simple random sample from each group. This is a stratified sample. B, obtain lists of patients discharged from all MMH facilities. Number these patients and then use a random number table to obtain the sample. This is a simple random sample. Randomly select some MMH facilities from each of 5 geographic regions and then include all the patients on the discharge lists of the selected hospitals. This is a cluster sample. At the beginning of the year, instruct each MMH facility to survey every 500th patient discharged. This is systematic sample. And E, instruct each MMH facility to survey 10 discharged patients this week and send in the results. This is a convenience sample. A few more definitions to wrap up for today. A sampling frame is a list of individuals from which a sample is actually selected. Undercoverage results from omitting population members from the sample frame. Sampling error is the difference between measurements from a sample and corresponding measurements from the respective population. This is caused by the fact that the sample does not perfectly represent the population. Non-sampling error results of poor sample design, sloppy data collection, faulty measuring instruments, bias in questionnaires, and so on. Multi-stage sampling, and convenience sampling. This is a copy. Sorry. We already talked about those. So that is all I have for you for today.